Welcome everyone, thank you for coming. So I'll be presenting on the computational resolution of the inverse problem of kinetic capillary electrophoresis to arbitrary actors. So I am a member of the Sergey and Krylov lab at York University. I'm a postdoc there. So that's at the chemistry department, but my degree is in applied math, actually, from Waterloo. So to give you a quick outline of the talk and the objectives, so I'll be giving some background on the problem first. This will be an inverse problem, so there is a direct problem. So I'll introduce that, provide some description and analysis of how I've been able to resolve the direct problem, and also introduce the inverse problem, analyze the computational performance that I have been able to achieve, and then show some example plots. So I'll be demonstrating the efficiency of the algorithm and all that. The papers that I've written on this problem are really stemmed in this kinetic capillary electrophoresis model. So this is a survey paper that's being cited here. So the three papers are, the first one is on the direct problem, so the efficient resolution of the direct problem. The second is basically on finding a reasonable estimate for starting the optimization. Why is
it's a smart screen, so
okay.
if you touch the screen,
touch it.
you bring it up the main software and everything. Now you can draw.
I'm screwing it up, right? Okay, whatever.
Yeah.
Hopefully I won't break it. Alright, so the third problem, so the second problem is finding an estimate to start the optimization, right, for solving the inverse problem. The third paper is on the actual resolution of the inverse problem. So the associated program package is available on GitHub, so anyone can take a look and download even. It's a package in MATLAB actually. So the outline of the talk, so I'll present the physical model, the direct problem, inverse problem, and then talk a little bit about the software package and the performance analysis. So the equations are the convection diffusion reaction equations. So we have diffusive term here on the right, we have convection here, and then the reaction term is, it can really take any form. So the reaction term can vary greatly, but the other terms are quite fixed. At least this is the equation we start out with, and then we sort of specialize that to the Nernst-Planck equation. So that's sort of an intermediate form, and then we get to the actual equations we need, which is the KCE, kinetic capillary electrophoresis equations. So this is actually a vector PDE. So we have a Hadamard product here. So it's for KCE it's 3 lines of equations, but the algorithm that we developed actually works for multiple substances, more than 3. So. But for KCE we have a ligand, a target, and a complex term, and then some constant velocities, diffusion coefficients, and this is what the reaction term looks like. So we don't have linearity, of course, otherwise it's an easy problem. And in order to ensure existence and uniqueness of solutions, we need initial and boundary conditions. So we have all kinds of cases, and these are not all possible cases, but these are ones that are experimentally relevant and that have been studied and actually carried out in our lab. So yeah, if you want, you can take a look at these, but basically they all involve some sort of a density function, some concentration constants, and all sorts of things. All right, so the direct problem is to efficiently generate numerical solutions to the KCE equations, this reaction term. And we can actually consider these solutions to depend on certain parameters. So we can either just consider k on and k off. You're actually looking for k on and k off, right? So what we can do experimentally is measure signals, which are not even the solutions. They are worse than actually having the solutions. I'll talk a little more about that here. But the point is to extract from the experimental signal somehow this k on k off parameter pair. So that's the main thing. But actually, there are other unknowns. So it's not just the 2-parameter inverse problem, but actually it's a 14 parameter which can be reduced to a 10-parameter inverse problem. So because these concentrations here, concentration coefficients, are also unknown. So actually, yeah, so in addition to this k unknown vector, or parameter vector, we also have this gamma, which is 5 components, and they are the parameters for the injected plugs, which are modeled as asymmetric Gaussian concentration profiles. So the signal is actually dependent on k and gamma, and actually it's a very bad signal because we take the sum, superposition, the sum of the first and third component of solution C, right? Because C is equal to LTC, the vector. So the signal is the sum, and we take a slice and the detector. So we don't even have it for all x values. So this is a very, very bad signal. A lot of information is lost or is actually not provided through this experiment. So resolving this inverse problem seems perhaps sort of hopeless, right? But it isn't. So anyway, let's take a look at the signal. So sort of zoomed in, you can see that this signal was actually simulated with the Dirac solver in the program package. So you can see that relative to the exact solution, the numerical and the exact solutions match up pretty well. And of course there is actual analysis of how well they match up. So the numerical solution idea is to change variables to eliminate the convection term, because if you're familiar with convection diffusion equations, the huge issue is that the convection and diffusion terms, the coefficients, sort of interact in a way that typical numerical discretization schemes become unstable, right? So in order to eliminate the instability, we can, in the constant coefficient case, in the constant convection case, we can eliminate the convection term and ensure perfect stability of the discretization scheme. So the requirements are, so it must be very fast to be practical for the inverse solver. So I'm talking about the direct solver generating each signal. And the inverse solver, of course, must finish within a reasonable time frame so that we can actually do a software development, right? You know, if it runs for, I don't know, like 3 or 4 hours, then we can't develop a package, right? So the solution should be also accurate in a quantifiable way. All right, so this is the runtime analysis for the direct solver. And we can see here that the exact solutions for a particular subcase, we can actually find the exact solutions. So with increasing mesh size, we have a linear increase in runtime, right? That's what we would expect for the exact solution, right? But for the numerical solver, which is based on a discretization scheme, with a certain mesh, we have a quadratic because the runtime depends on a quadratic relationship. Okay. So the accuracy decreases approximately proportional to 1 over I. And that's actually, so 1 over I is 1 over the temporal mesh size. So that's about delta T, right? And that's typical for convection diffusion equations. So the complexity of convection diffusion equations numerically is delta T plus delta X squared, typically, or order delta T plus delta X. All right, so to state the inverse problem, how should I do that? I started late, right?
Yeah, you did.
So maybe 25 or?
Yeah, sure.
All right. So the inverse problem statement, the parameter space, as I mentioned, is 2 plus 12 parameters, right? So 14 dimensions, but this can be reduced to actually 10 dimensions because of certain relationships that come from chemistry between the parameters. Okay, and this is actually pretty important because I didn't realize this at first, and there was an internal contradiction. So I was trying to optimize in 14 dimensions, but there was an internal contradiction as I was optimizing in the parameters, so that didn't work out. So I had to realize that I need to reduce the parameter space. Alright, so the error function looks like this. It's very simple. So we have a target signal, right? So that very overly simplified signal with a sum and a slice at the detector, and it supposedly comes from some omega star parameter. So omega stands for the k and gamma vector together, or actually the reduced vector. So this is the error function, and we have some d metrics. So I'm just using the typical L2 Euclidean. KCE inverse problem is so given a threshold epsilon and a target function, we want to minimize the error below that epsilon. Okay? So this problem is likely to be very likely to be opposed, exactly because of all that loss of information for the signal, and multiple solutions that are expected for epsilon equal to 0, exactly because of the loss of information. So, and also the well-posedness of this inverse problem is equivalent to the error function having a unique global minimum. So is that true or not? Well, I don't know, because my project has been solely computational. I haven't done any theory, so I have no clue if this is a well-posed problem, if we have a unique global minimum, but according to all computational experiments, that is the case. So we are very lucky, because this is a nice problem, right? A resolvable problem. So the inverse problem solutions project plan was the following. So it was resolved computationally in 4 main steps. So first of all, simulating solutions to the equations, so the direct problem, and then finding demonstratably reasonable estimates for the soft parameters. So that's the estimation, find an initial point to start the optimization at. And then guaranteeing a prescribed delta error in the parameters based on some epsilon error bound in the signal. Right? So we want to control the error in k. So remember, we are actually looking for k. We don't really care about the gamma, but that's a side product of the whole inverse problem. But we want to ensure that the error in k is controlled in a way by the error in the signal, so that it falls below a certain delta. So minimizing the error function below epsilon, starting at the above initial estimate. So that's the actual optimization problem, which in itself is also challenging. All right, so the initial estimation of the parameters. So for that, there have actually been previous papers by our lab. So there is an existing method called the area method, which sort of breaks the signal up into different areas, and there are some nice formulas, and you can get estimates for K on, K off. Yeah, so that's the area method. But I came up with my own method, which is actually derivative based. So when you have like a very noisy signal, you can't really take derivatives. So in order for the derivative based method, my method, to work, there has to be some sort of a smoothing or filtering of the noisy signal, and then apply this estimation method to get some estimates for K on and K off. But anyway, if we execute my method and the area method for a simulated, so sort of a perfect signal, then this is actually what we get. So a near constant, very low error for different K-ons, and the dashed lines are for the earlier area method. At least for this parameter range, this is what I got. So, I mean, it wasn't especially pre-selected or anything, I just chose some standard parameters. Okay, and then these are the gamma parameters. Remember, that was for the initial plot concentration profiles. So the center, left and right standard deviation, and the height of each asymmetric Gaussian injected plug into the capillary. So again, we have near constant errors, relative errors up to a certain point. So what is this point actually, right? So that was around 2.85 or something like that. And here again around that point. So that demarcation is approximately where the left peak, the C peak, disappears. And in my software, in my algorithm, I specified that in order to extract stuff from the C peak, the left peak, you have to be above it like 5% or something. So as soon as the C peak, the left peak, falls below that 5% from the maximum, the whole signal, then we start having crazy behavior. So, all right. So the next thing is controlling the error. So controlling the unknown error in K, right? So between the target K star and our current K through the error in the signal. So the solutions of this PDE, set of PDEs, is assumed to be classical. So we have continuous differentiability as many times as we need in the derivatives. So one time derivative and two space derivatives, continuous differentiability. So locally we definitely have some sort of a we should have a Lipschitz equality. So we suppose that there's an L here that this holds. So again, nothing is proven theoretically in the papers yet. So something for the future. So numerically, I can estimate this Lipschitz constant as follows. So I just divide over and maximize over some test points in the parameter space over a local compact picture. Right? Compact because we want to have a maximum. Okay? All right. So the program package is called KCE solver. So again, it's on GitHub if you want to take a look at it. So there's a direct solver, inverse solver. It's very nicely organized into folders. So there are these different estimation methods and the actual optimization of the error function. All right, so the next few graphs will be the actual analysis of the software package. The variation of the relative error. So for increasing K on, we want to ensure that for all cases we want to ensure that the relative error falls below 10 to the negative 4%. in the signal. So that's very, very low, right? I mean, we are setting a very tough mark for us to achieve with the optimization algorithm. And that's again achieved up to the sort of the point where the CP disappears, right? And then it goes crazy. Okay, and you can actually see here the variation. So that's where the CP disappears is around like, you know, this point. So, okay. So what I didn't talk about is what kind of optimization algorithms I'm using. So I'm using the BFGS and LBFGS. So that's the Broyden-Fletcher-Goldfarb channel algorithm, which is a quasi-Newton method. And actually, at the last CMS conference, or I mean, at the last winter CMS conference, I was suggested that I should try quasi-Newton, and that's actually what worked out very well. Much better than like the 10 other optimization algorithms I've tried. And they are actually built-in algorithms in MATLAB. FNCOM is the subroutine. So, so the target threshold again is very low, 10 to the minus 4%, and it's reached kind of up to 3.45. And it's correlated with the disappearance of the CP, the left peak. All right, and then this kind of shows the correlation between the signal and the K on error. So we should just, it looks really complicated, but just look at the middle black fitted line here. So what this shows is that as we decrease, so this is actually decreasing, it's kind of tricky. As we decrease the required relative error in the signal, the relative error in K on also decreases according to this line in log-log space. Okay, this is a log-log graph. So we have a nice decreasing behavior as we would expect, and then on the right we are plotting the runtimes. Okay, so I'm almost finished. And actually, an important point to make is that runtime doesn't significantly change or vary with the change in the mesh size. So we can, you know, for low mesh sizes like between 500 to 2000, we can easily vary the mesh size, and the runtime won't change significantly. So we shouldn't be shy about giving the algorithm some, you know, higher mesh size. Right, so these are just some plots in 2 dimensions of K on and K off. Optimization only, so no gamma, only K on and K off. With different algorithms. These are some biological algorithms. And then the BFGS and LBFGS. Kind of visually we can see what's happening, or actually not see what is happening. So again, completed papers. So I've introduced a physical model, described the direct problem, formulated the inverse problem. So that's about all I want to talk about. Some references.